This is a model building exercise which focus on modeling rather than just coding. So we are going to think about the biological observations before we start modeling. And this will be more code intensive, so a lot of edits in the Python steppables. And I hope you guys enjoy. We talked about yesterday cell growth and division, and all the cells were growing with the same rate. We know that this is not necessarily true. In many cases, the cells grow and divide based on the nutrients they have access to, as we also discussed about in the previous model building exercise, where the bacteria consume nutrients and divide, grow and divide, only if they have enough energy available. So the avascular tumor consists of multiple layers of cells, where the cells in the middle are the necrotic cells because they don't have enough nutrients available, so they cannot survive. There is a quiescent zone where the cells are unable to replicate, but they can survive. And the outer zone closer to the sources the of nutrient, they have enough resources to proliferate. So the tumor grows from the outside, and it's a self-limiting system because the cells inside, which are the majority of the cells, they die off pretty quickly. This is observed in both in vivo and in vitro. And but they are different, right? Because, for example, in vivo we have blood vessels, we have other cell types interacting, so they are not exactly the same. We can explore that. We can also ask how far does the nutrient, which we can interpret as a signal for the purposes of the simulation, how far does it get into the tumor, and how much does it take for the vascular tumor to grow? And what's the relationship between tumor growth and the nutrient field parameters, such as the replenishment rate, the diffusion coefficient, and the consumption rate? Because the tumor is a decaying region, the field gets that exponential profile that we explored in the first lecture. We built that exponential field profile with a fixed boundary condition and decay on the medium. This generates this exponential, which gives us a characteristic length. So the field penetrates the tumor up to a certain typical length, and this length is depends on the diffusion coefficient and the decay coefficient following this relation. The diffusion length is the square root of diffusion over the decay. So if the cells get access to enough nutrients, they can proliferate. If they don't have access to nutrients, they die. And in an intermediate range, they undergo quiescence, so which is a state where the cells are unable to grow or proliferate, but they have enough energy to survive. So we have state transitions that we will model by changing cell type depending on the concentration of our field. So the field is behaving as a signal that tells the cell to change type, to in a sense differentiate. It's not really differentiation, quiescent state. Yeah, maybe it is. I don't know. Um, but the first transition from healthy proliferating to quiescent, this is reversible. So a quiescent cell When it gets access to nutrient again, it can become proliferating. But if it dies, there is no coming back. So transition from quiescent to necrotic is irreversible. We'll choose boundary conditions. In this case, our boundary condition, like there are many possible solutions here. The one we are sticking to is the medium as a reservoir of nutrients. So medium will hold the field at a constant value. Um, yeah. And the boundaries, we can leave the boundaries as periodic boundary conditions. But the medium itself will be the source of the nutrient. Okay, that's it. Let's start doing it. So to set up the simulation, some basic configurations here. We need to set a lattice, 256 by 256, blob initializer, and then copy range 2. And we need three cell types, prolif, quiesce, and necro. We need a chemical field, nurture, with diffusions over Fe. And then we need contact, secretion, mitosis, and volume local flex. Notice here that I'm not selecting the growth behavior. I am not selecting the growth behavior. I am just selecting the mitosis behavior. Okay? We can simply type down the growth in the mitosis steppables, which in my opinion, it is easier and has less room for confusion this way. Finally, we need secretion. So go ahead and check that box, that secretion box. And if you don't see that secretion box, then you go CC3D plugins and secretion plugin on your to edit. And then you select medium to secrete a nutrient at a constant concentration of 100. This is something you can do in the Python, I guess. We'll see. So I'll give you some time to do this. I'll give you 5 minutes to set this up. This should be very quick, right? Because it's just clicking stuff on the wizard. However, I am too impatient and I will start now. So let me close this. CC3D project, new CC3D simulation. Again, this exercise you can access in the student materials folder. The code is there. Copy range equals 2, blob initializer, and periodic boundaries. Notice that I cannot set periodic on Z because Z is 1. Does that mean we change constant concentration field to 100 for a medium in chemical field initializer in wizard? If you're talking about version 4.7, yes, you can do that. Perfect. If you are on 4.6, I will give you other instructions. I was able to do that in 4.6. Okay. Interesting. because I have to confess something. I think the version I'm running here is like 4.4. I do use 4.6, but it's Python only. I guess I let me check. Let me try that. So new simulation, next, next, chemical field. No, no, I'm 4.6. 4.6 doesn't let you to choose this diffusion situation here on the wizard. If we select from properties, right here, pick secretion. Oh, okay, secretion. Yeah, yeah, yeah. Then here you can do medium secretion rate 100, constant concentration at entry. Perfect. Yeah. If you do this like this, yeah, yeah, this is absolutely fine. Absolutely fine. Okay, so I just set my general simulation properties. Next. Here, cell type specification, I'm going with prolif quies. Yes, Clara. And necro. So this is my cell type specification. I think I can go next. Chemical field neutr. Next. So here I need contact, I need secretion, I need mitosis, and I need volume local flux. Contact, secretion, mitosis, volume local flux. Okay. Next. Now secretion plugin here. So this is where you can set your medium secretion. We just go with next here and finish. Why am I skipping secretion? Because I want to show people how to solve this issue on the XML. Okay, so I have to set medium to secrete nutrient at constant concentration, 100. And how do we do that? So the exercise was originally intended for 4.6. So we need a workaround here. So what I will do is, let me put this to the side, and people who has the 4.7 up, watch what I'm going to do now. So see that I have the secretion plugin here, right? I have the secretion plugin. I will call it again. CC3D plugin secretion. I will replace, and it will give me a bunch of syntax. Okay. Here is where I will change things. So let me delete these comments. So here I have secretion, field name. I have cell type name for secretion, secretion contact, and a constant concentration. So the to edit is giving me three options of secretion here. Okay, let's do step by step. So look at me. People that are using 4.6 and already set that via wizard, you're okay. Now, people that didn't set secretion, pay attention here. First, field name. It has to be the same name as the in the diffusion solver. So field name, nurture, in my case. Okay, that's the first step. Second step, we want to have just constant concentration in medium. So these other lines that TrueEdit is giving us, we can comment them out like this, or you can also just delete them. And finally, on cell type, you can type medium here and then give it a constant concentration of 100. Then your plugin can look like this. I can also delete this to make it look simpler. And finally, I can also copy and paste this in the chat so that if you're having trouble including your secretion plugin, you can just copy and paste this into an open location in your XML. No, alignment is not important. If you get the constant secretion through the wizard, then should it appear in the XML? Yes. Yes, it should. Is the alignment important? No, you can do this. It doesn't matter. XML is, it just pays attention to the brackets. It's not like Python. It doesn't matter. Oh yeah, correct. If you use the page in 4.7 wizard that pops up after you add a field, it can also be added. So you can also set a secretion, but it puts under diffusion steppable under here, somewhere here, instead of in the secretion plugin, which is the correct way to go about it. So on 4.7, we are doing it correctly. That's supposed to be like, it's supposed to be like that. So after everything about 4.7 is fixed, we will abandon this kind of syntax and have just field specification or Python specification. Correct. So you can also do, for example, in your diffusion solver, you can also, an alternative way is to uncomment constant concentration and then have type medium, have constant concentration 100. Okay. This is also possible. Either you'll have it here on secretion plugin, or you have it here on your diffusion steppable. Osman, we still need a secretion plugin because eventually we are going to set uptake. And uptake cannot be set in the diffusion steppable, only in Python. And to set it in Python, we need to specify the secretion plugin. Okay, moving on to the next step. Now we'll have to do these changes. So set global diffusion constant to 10, set global decay constant to 0.01, comment out diffusions and decays for specific cells. We don't need these, all of these we don't need. Set initial concentration to 100 right here. So uncomment this line and set initial concentration. Comment out secretion lines inside the diffusion steppables if you set on your secretion plugin. If you are setting your medium secretion in the secretion data, then you have to be careful and comment just the other ones, not the medium secretion. Then you have to set both X and Y periodic boundary conditions. I wrote periodic boundaries to periodic. So both X and Y boundary conditions to periodic. And then in the blob initializer with 8, and then you create only prolif cells. With a certain radius, 51 is okay. You can also do smaller radius like 4, it doesn't matter. It sets up uptake in the secretion data part of the XML though, or is that just initial condition? Huh? It sets up uptake. Uptake is not set in the XML, only in Python. Which lines need to be commented in secretion in XML? If you are on 4.6 and you set your secretion diffusion, your secretion inside the secretion plugin, then you comment all of them. If you are on 4.7 and you are setting your secretion inside the diffusion solver, then you should be careful and just comment out the cell-specific ones. So in my case here, because I'm setting a constant concentration on medium inside my secretion plugin, I'll just go ahead and delete all of this. So I don't have a secretion data in my diffusion field. If you are on 4.7 and you are not defining your secretion here, then you should leave that line. Yeah, so if you are on 4.6, do as I do, delete everything in the diffusion solver FE that are related to secretion. And leave just the setting inside secretion. Kaya. Can you just repeat everything in the diffusion plugin again? Yes. So I will uncomment this. So I think you are on 4.7. So if you are on 4.6 and you set your secretion parameters inside the secretion plugin, then you just delete all the secretion data you have on your diffusion steppable. If you are on 4.7 and you did not you did not specify your secretion inside the secretion plugin, if you specified your secretion inside the secretion data, medium here, constant concentration, medium 100, then you get rid of the cell-specific secretions like so. The diffusion data, so it is telling us to comment out the diffusions and decays for specific cells. So you can get rid of these lines here. Where is initial concentration at? Initial concentration is this line here. It's commented out. In my case, line 73. If I press Control slash, then I can set 100 here. That's our initial concentration. Are you guys following? Finally, setting periodic boundaries to periodic, setting the boundary conditions to periodic. So I'm going to comment out these lines here and uncomment periodic, just as we did in the other exercise. Again, if you don't have the periodic command, just copy and paste. Max uptake block as well. So apparently in 4.7 there is an uptake block that I didn't know about. Uh, yes, please comment that out too. It's very interesting that now we have uptake inside the diffusion steppables. Unfortunately, the 4.7 version is recent news and things take a while to adapt. So these lectures are not designed specifically for the new changes of 4.7. And since we are having problems with 4.7, it's not very worthwhile to switch everything now that we have many people on 4.6. So yes, if you have that, go ahead and comment that out too. Finally, on our blob initializer, we are setting with 8 and creating only prolif cells. So these ones go away like that. And again, if you are not following very well, oh, this is very good. This is very good content here. Uptake, max uptake, relative uptake, cell type, all good stuff. This is amazing. So big improvements for 4.7. It's a shame that we are running on, onto those bugs. All right. Uh, this is all good stuff. Let me run the poll. See how you guys are doing. Exercise completion poll. Okay. Now let's see if I got the right poll going on. Why have we removed other cells? Suvani, why have we removed other cells? Because it's said in the slides. You don't need to do that if you don't want. It doesn't really matter because that's just initial condition. The overall behavior depends on the initial condition for this simulation specifically. So so we should comment out what Seema sent. Yes. Yes. I mean, uh yes. Yes, you should. I was trying to think of a way of making that work, but unfortunately for this model, we have to specify everything in Python. Okay, next step. In the constraint initializer, set target volume 64, lambda volume 8. So this is where? In the steppables. So no XML anymore. If you've done this, Kaya has a supposedly stupid question. I'll read the supposedly stupid question out loud so that everyone knows. So if initial conditions aren't specified for a cell, it's automatically zero. Correct. It is automatically zero. That's not a stupid question, in my opinion. So now I go to the steppables and look at this. We have a constraint initializer here. See? In this constraint initializer, we are setting target volume to 64 and lambda volume to 8. Now, in the mitosis tappable, set cell volume threshold of 128 for division. So, scroll down to mitosis tappables. Cell volume greater than 128. And then delete or comment out these four lines which change cell type upon division, like so. So basic cleaning up the stappables here, setting initialization constraints. Can you elaborate the mitosis stoppable, please? Yes. So the mitosis stoppable, we have to set a volume threshold of division to 128, which is double the normal volume of the cell, the initial volume of the cell. And then in the update attributes function, we had this piece of code here, which changes the cell type. And just go ahead and delete it. When we set initial concentration as 100, isn't that setting medium concentration also to 100? Why are we doing this twice? Ripla, we are doing this to set 100 at the tumor cells, because if they start with concentration 0, they will die instantly after we create the conditions of switching to cell death, etc. That's why. When we tell the cells to die below a certain nutrient concentration, we will instantly lose all cells if we don't initialize the field at 100. Okay. Moving next. Moving on. Run. So let's make sure everybody is getting this behavior. So we have cells growing like this, and then if we take a look at the nutrient field, okay, something is wrong with my simulation. Okay, I know what's going on. I didn't set any decay inside the cell, and here the simulation has some decay. So, oh yeah, set global decay constant to 0.01. I think I didn't do that, did I? Global decay constant, 0.01. Let me run that again now. Okay, makes sense. Fantastic. So the cells are growing fine, and then they are consuming. And you can see that naturally the borders have higher concentration than the interior. Harini got it right. So make sure you guys got to this part. I'll leave this last instruction, launch the poll, to see how you guys are doing. Relaunching poll. Global diffusion constant 0.1. My field is not a gradient. Your field is not a gradient. Your field is a scalar, Eva. So correct. Your field is not a gradient. Your field is a scalar. Growing very slowly. Is it fine? Maybe. I don't know. Maybe it's fine. How do we change the color? Mine is just appearing as blue. Probably you did not set an initial concentration of 100 everywhere. Juhi got it right. Clara, can you show your sim running one more time? Yes. So here it goes. One more time. I mean, my field is just all red. So probably you need to set higher decay constant, like 0.01. Got it. Can't share here as I am doing it on my desktop. Thanks, Pedro. Okay. Global decay is set. Initial concentration is set, but again, all red. Same here. Mine becomes blue real quick. Try decreasing decay coefficient. The blue part just freezes, and I don't know why. The blue part freezes. Double check your growth rate to make sure it is not too high, and also your volume constraints. So, Derek, you can from now on ignore my presentation and work on the nutrient-based growth, where the cells, where you control how fast the cells are taking up the nutrient in Python. So it's not pure decay, you introduce uptake. And their growth rate is given by the amount of nutrient they are taking up. I also get all red when it runs for long enough. Check if you don't have secretion of nutrient at the cells. Maybe you have secretion of nutrient at the cells too. You can also go to Tools, Configuration, and check here if your min and max are between 0 and 1. I would suggest you do that. Fix 0 minimum and 100 maximum for this field. Try that. And I will proceed. So for the next step, while you guys are working on current issues, I will start talking about the next steps. So we'll have to change the cell types. So the cells have to transition between states according to the concentration of nutrient. If the nutrient level the cell is exposed to is below a threshold T1, it no longer proliferates. If it is below another threshold, it will die. So we have two thresholds. We have threshold 1 and threshold 2. Okay? Uh, Quiescent cells can proliferate again if the nutrient is high enough. So there is another threshold there. Can be the same as the first threshold, but in general we set it a little bit higher. Um, Otherwise the cells can like be blinking between states. Yeah, so this is what we have to do. So to do that, you will loop over all cells in two separate loops. One loop over cell types prolif and another loop over cell types quiesce, which you can import from CC3D Python visit and then all cells of given type, which I'm going to do here and paste on the chat. So CC3D project and then visit all cells of given type. So you can do this. And then this is the code you're going to get. And next, you are going to get the concentrations. And based on the concentrations, we are going to switch the type of the cell between proliferating, quiescent, and necrotic. The final code will look like this, and I will screenshot this and paste on the chat. And while people that are a little bit ahead try to follow these instructions, I will debug issues that people are having in the chat because it looks like many people are having issues. Can we do a debugging session? Perhaps uh, Clara or Noshin could screen share and I can go through the code so everybody can see what the issue is. Rodrigo, where should we add the new part of the code? Where do you think? Where does this go? Yeah, the class itself doesn't matter. It can be inside any class, but it has to be inside a specific function, a step function. Okay? So who volunteers to share screen and show me the error? People that got this all blue situation. First, you have secretion constant concentration medium. Okay. Scroll down. Scroll down. More. Scroll up. Okay, show me the simulation running. Sorry, this is Ripple screen. Uh, okay. Uh, huh. Interesting. Uh, so first do something. Go to tools. You have to first run the simulation and then you pause the simulation. Tools, fix. Okay. Okay. Uh, what? Go back to your code, XML. Okay. So you are on 4.7, I believe. So remove this line 53 where you have constant concentration. Remove that. And then go to secretion data and uncomment constant concentration medium 100. Save and run. Medium is with uppercase M. Save and run. Solved. I hope that the others saw what we did. So basically what we did was remove the specification of secretion in the secretion plugin and activate it in the diffusion steppables. That's for 4.7 only. The other ones running 4.6, you guys are okay. So Ripla knows exactly what to do, so I will trust you to help the others if they are still struggling to implement those changes. You can also copy and paste on chat exactly the lines that you changed so everybody can catch up. All right, coming back to this, I'll go over the instructions again. Import the syntax for looping overall cells of a given type. This goes in a step function. So, huh. And we have a bunch of stuff ready to go here. We have an example code here. This is nice. Very interesting. So here, CC3D Python, visit all cells of given type. It gives us this loop for cell for cell in self dot cell list by type. And here we give it a name. So we have a loop over prolif cells. And then we need another one. We can delete this comment. And then we need another loop over cells of type QES, like this. Oh, this is not properly indented. Now it is. And next, we are going to measure the concentration of the field. There is sample code here that I can just copy and paste. But instead of doing that, I will use the to edit code snippets because it's generally more useful. So CC3D Python, chemical field manipulation, get field reference. So get field reference, we are getting the object of the field. It has to have the same name as the field in XML. So my field in XML is nutr. That's the name of the field, which is the name I have to give in the Python. Now I have to get the concentration of the field at the cell center of mass position. So first I will come again to the code snippets. CC3D Python, chemical field manipulation, get field value. And I get this syntax over here. Now, I will give coordinates for this field. So this is X, Y, and Z coordinates, okay? And what are the coordinates I'm going to pass? The X position of the center of mass of the cell, which we access by typing cell dot X and then uppercase COM and analogous for Y and Z. X, Y, and Z in this order. So this is our concentration. Concentration at center of mass. We can get rid of this print and then we can copy and paste and have two similar loops, except that one is over prolif cells, the other one is over QES cells. Pedro, could you please repeat the last step? Yes. The last step was. I come here, create a new line on the for loop over cell type prolif. Then I come to CC3D Python, chemical field manipulation, get field value. It gives me this syntax. And here, instead of 10, 10, 0, which is arbitrary, I am passing the coordinates of the cell. So cell.x com, cell.y com, cell.z com. And then I am copying and pasting this on the other for loop because we're doing the same thing on both. And then I can get rid of the sprint. Are you purposely leaving in target volume increase? Yes. Okay, next step. If concentration is lower than 70, switch prolif cell to quiesce. So here I'm going to test. If the concentration is lower than 70, then cell type becomes quiesce like this. Else, cell dot target volume plus equals 0.5. So at this point, we have our target volume increase conditioned to the cell being prolif and having concentration value above 70, which means we can get rid of the cell growth. So now I'm commenting out the cell growth up here and leaving cell growth just inside the for loop over cell type. Now, if concentration is lower than 40, switch quiesce cells to necro and set target volume of the necro cells to 0. So here we are going to do if the concentration value is lower than 40, then we do cell dot type is necro, and then we do cell target volume equals 0, so that the cells shrink. They shrink and disappear. Now, if concentration is higher than 70, switch quiesce cells back to prolif. So if value is greater than 70, then we do cell.type equals self.prolif. Yeah. And let me see if that's correct. I'm just gonna run this to see if I got the right stuff. And it seems like I didn't because it just crashed. Has no attribute prolif. Oh, I wrote profile prolif. Oh, I forgot to set the decay. Not good. Too high decay, 0.001. I think okay, I'm not creating only prolif cells. That's one problem. Uh, okay. Something's not right here. Field cell. Okay. Target volume 0 for necrocell. Hmm. Let me decrease. Oh no, growth rate is fine. Maybe I didn't set the proper diffusion coefficient. Oh, diffusion constant 10. Okay. Let's see if the suspicion is correct. There are just too many prolif cells. And it's not being taken up fast enough. 0.01. Okay, I didn't set the correct decay coefficient. 0.01. Parameters matter a lot. Now, let's take a look at the cell field. Now I have my quiescent cells, the necrotic cells. Okay, that's it. Osman, yes, you can. This is topic for one of the other lectures. And I'm setting two constant concentrations. Yes, this is also not ideal. I can delete this one. I don't think it's going to change anything, but that's a well taken point. Okay, so this is working. We have 20 minutes left, and on the 20 minutes left, we are going to do nutrient-based growth. So here we have 0.05 of volume increase. We want to condition this to the amount of nutrient taken up by the cells. So first, gross double has no attribute prolif. Did you mean are you doing self prolif like this with uppercase letters? It has to be uppercase letter, all uppercase letter. Uh, does anyone know attribute, no attribute prolif? Make sure you have a cell type with this name in your XML. Make sure you are doing self.prolif too. Yeah, and it's self.prolif, not cell.prolif. Okay. The second one is wrong. This one is the right one. Okay. I will launch the poll to see how you guys are doing, and I will show the instructions for the extra exercise, which is nutrient-based growth. So nutrient-based growth, we are doing uptake inside the tumor cell instead of decay. Why are we doing that? Because with uptake, we can keep track of the amount the cells have taken up. And by tracking the amount the cells have taken up of nutrient, we can condition the growth rate to that value. So make the growth rate be proportional to the total amount of fuel taken up by the cell. You can get the syntax of the total amount taken up by a cell via CC3D Python, uptake, and then total amount. If you do that, you get this syntax here. Sorry, this is total field integral. This is not what we want. Yeah, we want to do so it's uptake inside the cell. Oh, right here, total amount. We got it. So when you select uptake inside the cell, it gives you the syntax, which is uptake inside cell total count. And this total amount here is the amount of field a cell has taken up, which you can track. So this is the variable you acquire. And then you use this amount here to multiply this. However, it has to be minus total amount because this is a negative value. And of course, this guy has to go inside the the for loop. And per-leaf cells also, quiesce cells also take up nutrients. So you can do that. It's also recommending that we divide this value by like 100 because it's a very high value. And we track the field. Of course, now that we have show the whole line, please. This one. Now that we have uptake in Python, we can get rid of decay. So we can set decay to 0 and have only uptake. Let's see if this is still working. I could have made a mistake, so let me run this again. Secretor is not defined. Well, I have to define a secretor. So CC3D, secrete. This is the secretor. I have to give it the field name, and then it should work now. All right, it's working. And it's surely working differently than the others. The proliferating cells are growing. Do we need to set the secretor? Yes. I'll copy and paste this piece of code here on the chat so that if you are not following along, you can just copy and paste everything I did. But we also want to track how much nutrient the cells have taken up. And for that, CompuCell provides us with the tracking fields capability, which we are going to implement now. So I will go over the technicality of tracking fields. So tracking fields is basically you create a new field. You can create fields from Python, and you create a field with a scalar. It can also be a vector field, but you here in this case we're creating a scalar field from a variable that we are actually measuring during the simulation because we don't know beforehand how much nutrient the cells are taken up. So we will create a field that represents this number and we can see that happening during the simulation. So here in the steppables, we will have to create this field object and then give values to this field. Sounds complicated, but we have all the syntax available in Python. I will leave the slide aside because I think it will be clearer if I just show you how to do it in the Python. So here, yeah, so if a nutrient doesn't exist, check in your XML if you gave the same name to your diffusion field. It has to be the same. So here, to set up a tracking fields, we come here specifically Python, then there is a extra field, and then we have a scalar field cell level create. And it's telling us that we have to create this in the init function. So I'm going to place my cursor here in the init function. And I'm going to go CC3D Python, extra fields, scalar field, cell level, create. So this is the syntax to create a field. And I will call this field nutrient taken up. Okay? Now we have to populate this field. We have to give the values. And we are already measuring these values because in each of these total amount variables we can just pass this value as values to our field. So I'll place my cursor here and go back to CC3D Python. Where am I placing my cursor? Right below where I'm measuring this total amount. This is where I want to give the value to the field. So now I'm coming here to CC3D Python and then extra fields, scalar field, cell level, right. Here I have to give it the same name, and I can pass these field object. Oh, notice that there is a problem here. I'll pass this field object up here. So now you can see clearly that I have two variables named field, which is a problem. So I will rename the second field. I will call it uh, the the tracked field. Now this tracked field object, I have to change to that name over here where I'm changing the value of the field. What is the value I have to give to the field? I have to give this total amount. But we also have to clear the field before we do this. Otherwise, we are basically painting the lattice with field values. We always want to reset the value so every Monte Carlo step it refreshes to 0 and then we paint again. So now I'm going to go back to extra fields, scalar field cell level, and clear. So it's just this method, dot clear, that we need. And we apply this method to our tracked field. So it becomes like this. Tracked field clear, we clear the field, and then we assign a new value to the field right here. Why do we need to clear the field again? We can just reassign a new value. Good question. So I will give you an example of why we need to clear the field. Imagine that your cell is here and it has value 1 in it, and the rest of medium is value 0. As your cell walks to the right, if you do not clear the field, all this path here will have value 1 in it. So we have to clear the field and reassign so that the cells are not painting everywhere where they go through. Good question. So it's because cells move around and they would leave patches of field. Let me run this and see if it worked. And if it worked, then I will copy and paste these code. So I'll pause my simulation right here. And since we created the field, when we select our visualization, we can click nutrient taken up. And as we can see, it's not working. So let me first take a look at my configurations. Okay. Okay, let me think through this. We are creating a nutrient taken up, and then we are getting the field here. And then we are doing field clear, we can do right here. Then we have tracked field cell total amount. Let me run this again. What happened here? I think it crashed. For cells. Sorry, I need to move a little bit faster here. So I'm gonna try a couple of things. Oh, I know what's going on. And it's not wrong. It's correct. However, when I go to tools and I unfix my minimum, you can see now that my field is negative, and because I have a minimum of 0, I wasn't able to see the field. And why is that happening? Because the total amount is a negative value. Again, uptake is from the perspective of the field, which means that it's a negative value because the cells are removing material from the field. Now to correct that, what I will do is first fix to 0 here again, which means I don't see anything. But I will copy and paste this part with the negative total amount so I can keep track of exactly that multiplicative part of the field. And here we can see what are the cells consuming. And if I fix this guy, because this is getting out of hand, if I fix this to 3, I can see how much nutrient the cells are taking in time. And you can see that the cells that are more like more on the outside are taking more field than the other ones, I guess. No, I mean when the tumor is shrinking, they get more like red, and when it's increasing, they're getting more like green. I guess it's because they divided. When they divide, they are just taking up some nutrients, so it refreshes the counter, and they start getting red, and then when divide, they get green again. This is not like super informative, but it is for other kinds of simulations. Mine wasn't. So this is working. I will copy and paste all these here. This whole class. I'm copying the whole growth steppable class. Oh, there is a limit. Why? Why? Okay. So I'm going to paste only this in it. Now the step. The step is too big. Okay, let me remove this part. This is not necessary. All right. So these are the two chunks. Copy and paste chunks of it. Yes. Uh, Mine wasn't working either. Glad it wasn't just me, few. This would only do it in prolif cells though, right? I'm not sure what you were asking. Do you maybe have to capitalize the nutrient field? No, no, I don't. Maybe a minus before the total amount so that it is a positive value? Correct. And why didn't I look at the chat before? Because I was probably freaking out. Clara in line 31. Yeah, I don't know what line 31 was before. Should it be something like get field? Maybe. Please, may you copy and paste your code again. A bit behind from debugging. Yeah, I just did that. You only have self.nutrient taken up cell in self.prolif cells. Correct. And we can do that on the other ones. So we can do this right here. And now we are populating our field even more, which is a good point. Let's see what happens. So now we are also seeing the quiescent cells taking up the field. So they are greener in the middle, looks like. On average, they are greener in the middle. Yeah, yeah, I guess. So with that, I think it concludes my lecture, the avascular tumor simulation. There are lots of things to play with here. I particularly like this simulation very much because it gets to weird shapes. And here, the challenge, the homework is to get it to stay as a sphere. That's the homework. How would you change this simulation so that your tumor spheroid is actually a spheroid and not this amorphous thing growing and shrinking, growing and shrinking? How would you go about that? Hmm? That's a good homework. And I'm going back to the slides. If you want to know more about tumor and cancer, uh, take a look at Douglas Hanahan paper on hallmarks of cancer. You see lots of interesting mechanisms that uh, enhance cancer survival. And yeah, this could be a fantastic hackathon. Like you include a few of these into the avascular tumor, and that's an amazing hackathon project. Other than that, Hayden will launch the questionnaire. Please fill out the questionnaire poll, and I will see you tomorrow. We'll stay here for 20 to 30 more minutes for Q&A. So feel free to ask on the chat. If you want, you can download the simulation from the student materials folder. And also we can do debugging sessions if you need to show the code, see what's going on. We can take a look. Yeah, so Rocio has an error. Yeah, of course. We can help you with that. So Hayden, are you there? Can you launch the poll?
I
All
already
right.
did.
Okay. Oh, maybe I closed it and thought it was okay. Can Rocio screen share?
Yeah,
Uh,
Rocio, if you try to share, it'll give you an option to ask for permission.
right
There we
there.
go.
Okay. Let's take a look. Uh, can Rocio? It's awful because the person that is sharing doesn't show up in the in the participant list. So I have to open the participant list. I have to ask to unmute. Okay. File secretor total count expected three arguments got four. Okay, so go to your stappables. Uh, okay. So this should these total amount has to be a uptake instead of secrete. So if you see line 43, you have secrete inside cell. It should be uptake inside cell. And same for 47. Yeah, that should do. So I know where you messed up. When you go to CC3D Python, uh, CC3D Python secretion uptake, you selected um, secrete inside cell instead of uptake inside cell.
Sorry, where? Here?
Yeah, it's running, it's fine, right? So,
Okay.
yeah, okay, let it run. Let's see if it's all, I mean, it is all fine. Now it's working. We have a question from Anastasia. Could we also take a look at my bacterial ecosystem simulation if there is time? Yeah. Yeah, go ahead. You can share your screen. Anastasia.
Hi, thank you. Um, should I run it? I can show you. I don't know if it looks quite right, or do you want to go through
Go ahead.
the definition? Okay.
Go ahead. Yeah. Open player. So you're trying to implement in the code.
Mm-hmm.
Okay. This is looking good so far.
It doesn't do any of the shapes that yours is doing.
First of all, I think you did not implement cell death because I'm not seeing those bacteria be dying.
Oh, you know what it is? I have cell death as a function of energy, but I now realize that my energy never goes to zero. My energy just keeps increasing.
Oh,
So I
that's
don't
it.
think right
Yeah.
now, yeah, if I can show you,
Yeah.
um,
And this
because I
is
think
this
I'm doing
is
something. Sorry.
so if you look back to your pseudocode, you'll see you have energy decrease there, right?
I know. So I'm having a lot of trouble with the energy term, and sort of how to make it I mean, I can show you what it is now. So
Why
I
do you
do have
have
like,
pi on the code?
oh, it
What is
was to
pi doing?
constrain the surface.
Oh, okay. That's not
Um,
not the way we do it, but okay. Okay, keep going.
oh, really?
Yeah.
Okay, sorry. How would you do it? Is there like, would
We
you do the numpy?
the target surface we do 4 times the square root of volume because
Okay,
it's a square lattice. So
okay.
pi doesn't really work,
I see.
unfortunately.
Wait, so you would do here, what do you say you would do?
4 times square root of volume.
Squared of volume.
My tumor
Okay.
simulation, I have 3 different cells. No errors by my tumor.
Um,
Uh,
I can substantiate,
okay.
but basically this is how I'm defining the energy, and it's
Mm-hmm.
I kept trying to plot the energy with different sort of configurations, but I can't find like a good balance of how it should be decreasing, how it should be increasing as a function of the nutrient and waste.
This is the key challenge here. It's finding the parameters that give the behavior that you want. This is the most difficult part of the simulation, this particular simulation. And if you download and look at the simulation that I built, the values are like 0.036, to
Hmm.
find the right balance. It is a tough challenge. So I would advise that you uh, keep going.
Okay, I will.
Yeah.
Thank you.
But you are on the right track. This is looking great. Ripla, if you want to share your screen, let's take a look. Okay. Oh, right. Okay. Okay. Okay, go back to your Python subgoals. Go up, go down. Okay. Oh, cell target volume. There should be a point there. Cell dot target volume on line 55. Yeah, that's it. You're like defining a variable instead of changing the target volume. Now it should be now it's fine. Yeah,
Awesome, thanks.
no worries. Mark, could you please upload the final version of the tumor code? Drives one is not as complete as the exercise did today. Oh, sure. Yeah, of course. Of course I can do that. So let me show you because this is not named correctly. So what usually I do is save CC3D project as, and then I do a vascular tumor nutrient-based growth, giving a name. Not on garbage because it's not actually garbage. Okay. Now you can see that it has a different name here, the project. Now I can zip it, save a vascular tumor nutrient-based growth, then internet, day 3, student materials, demo codes, day 3, right there. So thank you, everyone. I will see you tomorrow on the 4.3 section. We have more modeling exercises.